Welcome to the Explainer. So today, we're going to completely change how you look at a concept you probably think you've already got figured out. I'm talking about estimation. We're diving into Cambridge Mathematics, Chapter 9, and right off the bat, I really want to shatter a huge misconception. Estimation? It's not about wild guessing. It's definitely not just throwing a dart at a board of numbers and hoping for the best. Actually, as we'll see through the logic in this material, it's about profound clarity and incredible efficiency. It's about taking the shape and size of the real world and applying math to make that world, well, manageable. All right, let's dive right into this.
Okay, so here's our roadmap for today. We're going to move from physical benchmarks into the strict rules of decimal places, and then significant figures. And finally, we'll cover rapid calculations and wrap it all up with sensible accuracy. Simple enough, right? Let's get to it.
Starting off with physical benchmarks. So how exactly do we measure the physical world around us when we don't happen to have, a perfectly calibrated ruler or a laser measure just sitting in our pockets? Well, this is where true estimation really begins. Picture this. You're walking down the street right now. If you had to estimate the height of a standard lamppost, right this exact second, where would you even begin? If you just tried to pull a number out of thin air, you're going to be wildly inaccurate. You need a tool. Basically, you need a benchmark. And this visual brilliantly illustrates exactly how we do it. By using a known benchmark, in this case, an adult person standing right next to the lamppost, we suddenly have a super reliable measuring stick. The source notes that a standard adult's full height is roughly 1.7 meters, and, their waist is about a meter off the ground. So, if we visually stack that person on top of themselves, we can see the lamppost is about 4 times taller. 4 times 1.7, that gives us a highly sensible estimate of roughly 7.5 meters. The text even points out that literally any answer between 6.5 to 8.5 meters would be totally acceptable here. The absolute crucial point is that we didn't just guess. We compared the unknown to something we already knew. All right, moving from the physical space of things like lamp posts into the realm of pure numbers, let's establish the absolute rules of rounding, starting directly with decimal places. If you've ever felt even a little bit unsure about rounding, let's lock down the algorithm right now, because it is beautifully simple and honestly incredibly rigid. Step 1, find your target decimal place. Step 2, look immediately at the next digit to the right, your next door neighbor. Step 3, if that neighbor is a 4 or less, you leave your target digit exactly as it is. But if that neighbor is a 5 or more, you round your target digit up by 1. And here is the most important part. You then completely ignore every single digit further to the right. They literally just vanish. Let's see this in practice. Say we have the number 9.368, and we need it to 2 decimal places. We find the second decimal place, which is the 6. We look next door to the right, and boom, we find an 8. Because 8 is 5 or more, it forces our 6 to round up to a 7. That 8 vanishes, and we are left with a crisp, precise 9.37. It's a binary, unarguable rule, no exceptions. Okay, so now let's tackle significant figures. This is kind of the concept where people often get tripped up, and it's mostly because it entirely shifts our starting point from what we literally just learned about decimal places. See, unlike decimal places, which obediently start counting right after the decimal dot, significant figures don't care where the dot is. Significant figures are counted from left to right, starting from the very first non-zero digit you encounter. That first non-zero digit, that's your most important, most significant number, because it dictates the entire scale of your value. Let's contrast them directly to be super clear. Decimal places start right after the dot, but for significant figures, leading zeros do not count. So in the number 0.005, those first few zeros are just there to hold the place value, to show us we are dealing in thousands. The very first significant figure is actually the 5. However, and this is key, any zeros trapped in the middle of a number or added at the end to maintain the sheer size of a whole number, those are absolutely crucial placeholders. Now look at the danger of rounding large numbers. Say we want to round 52,617 to 2 significant figures. Our first significant figure is 5. Our second is 2. We look next door at the 6, which tells us to round that 2 up to a 3. So we have 53. But wait, we can't just write 53. 53 is wildly different from 52,000. Actually, as the source text warns, a super common error is using the wrong number of zeros. We absolutely must use zeros as placeholders to maintain the magnitude of the number, giving us a final answer of 53,000.
All right, with those core rules locked in, let's see how estimation transforms from just a simple rounding exercise into an absolute mathematical superpower for tackling complex calculations instantly.
Imagine you're in the middle of an exam or, I don't know, out at a hardware store, and you suddenly need to calculate 47 times 63. Your brain might just freeze. But the golden rule for estimating calculations is to first round every single number to exactly one significant figure. So 47 becomes 50, 63 becomes 60, and suddenly that intimidating problem turns into an instant mental math equation, 50 times 60, which is 3,000. And the exact same logic applies to decimals, too. 3.7 times 2.1, that simplifies effortlessly to 4 times 2, which gives us 8. Easy, right?
So why do we actually do this? Well, this method provides a super fast, reliable rough estimate that acts as kind of a safety net. If you plug 4.7 times 3.9 into your calculator and accidentally hit a wrong button, resulting in, let's say, 183 instead of 18.3, your estimation safety net, knowing that 5 times 4 is 20, instantly tells you your calculator answer is completely off track. It's basically a built-in alarm telling us if our calculation is mathematically sound or just total nonsense. Which brings us perfectly to our final section, sensible accuracy. We know how to round, and we know how to estimate. But what exactly does it mean for a final mathematical answer to be sensible in the real world?
The source gives a fantastic real-world example for this. It points out that giving unnecessary degrees of accuracy is both unhelpful and honestly illogical in daily life. Like, it would be utterly silly to tell a friend that your standard train journey took exactly 4 hours, 46 minutes, and 13 seconds, right? It's much more sensible to just say it took about 4 3/4 hours or almost 5 hours. Math isn't just about raw precision. Context matters.
Now, check out this highly specific number on screen right here, 2.4288 square meters. I mean, it looks incredibly precise, doesn't it? It looks like the work of someone who really, really knows their math. But as we just said, context is everything. Let's uncover the story behind that exact number. A student in the textbook, named Bilal, measured a table's length and width. He used a standard measuring tape and got 1.84 meters and 1.32 meters. Now notice that is just 2 decimal places of accuracy. But when he multiplied them together on his calculator, he wrote down the area stretched all the way out to 4 decimal places, 2.4288 square meters. And this brings us to a massive, massive takeaway. Bilal's answer violates a core rule of mathematics, which is beautifully summarized in this quote from the text. The answer you give after a calculation should not be given to a greater degree of accuracy than any of the values used. Basically, your final result cannot magically become more accurate than the raw, messy measurements you started with. Because his initial measurements were only to 2 decimal places, his final answer should have simply been rounded to 2.43 square meters. Anything more than that, it's just fake precision.
Let's bring this all together. To truly master estimation, you need to use known visual benchmarks to measure the physical world. When dealing with abstract numbers, round to one significant figure to instantly unlock those rapid mental estimates. And above all else, always, always match your final accuracy to your starting data to ensure your answers actually make sense in reality. So I want to leave you with this final thought for today's explainer. In a modern world that is completely obsessed with massive data sets and hyper-precision, is true mathematical intelligence knowing exactly how to calculate every single decimal on your calculator? Or is it knowing exactly when to stop? Think about it. Thanks for joining me, and I'll catch you in the next explainer.